All right, welcome to the deep dive. You know the drill by now. We grab a stack of sources, we get into the core research, and we try to pull out the insights that, really matter.
And today, we're tackling what might be one of the most critical challenges in modern clinical practice,
Which is,
effective medical decision-making. I mean, we're in a world that is just drowning in data.
it's not an exaggeration, is it? The complexity is just, it's becoming the enemy of safety in healthcare.
It absolutely is. You have clinicians facing this exponential increase in patient data, super intricate medical histories, all these specialized test results. The pressure to make a quick but also accurate decision and to, avoid errors is just immense.
And the traditional model, the sort of lone doctor figuring it all out, it feels like it's buckling under that pressure.
It is. And that's exactly why we're seeing this profound shift in how we're even thinking about artificial intelligence. We're moving AI beyond these theoretical academic models.
Right, the stuff that just stays in the lab.
Exactly. We're moving to practical, deployable systems that are designed to fundamentally change the workflow and really just reduce that friction and that chance for error.
Okay, so let's unpack that intersection because we've analyzed two really major, I think, groundbreaking pieces of research here. And our mission for this deep dive is to connect them conceptually.
And it's a fascinating connection.
It really is.
Exactly.
So the first is a prototype study we've been tracking. It was published as the development of a conversational artificial intelligence-based web application for medical consultations.
Which is a mouthful. Internally, people just call it the RoboDoc prototype.
The RoboDoc prototype, right. And the second piece is an application that's focused on an explainable vision transformer model for detecting colon cancer. So our goal today is to trace the exact moment that one concept, the AI clinical cascade, which was first laid out in that triage work,
In the RoboDoc paper.
became the fundamental strategic blueprint for the much more advanced vision model that came later. It's like watching an idea echo and evolve.
And what's so fascinating here is that we're not just comparing two different gadgets or two pieces of tech. We're really analyzing a complete conceptual shift.
A framework shift.
It's a whole new framework. We're exploring this hybrid model that, structurally links three really key pillars.
Yeah.
You've got automated diagnosis, which does the initial heavy lifting.
The first assessment.
Then you have AI-assisted triage, which is the crucial step of assigning risk and routing the patient. And only then, at the end, do you have human medical attention.
The final personalized care.
Exactly. And that convergence, that structure, it tells us that the future, the scalable role of AI in the clinic isn't just about getting a higher prediction score. It's about creating a standardized, structured, and just an inherently safer workflow that manages all that complexity we talked about.
That structural framework, the cascade, that's our focus. It's the connective tissue. So let's start at the beginning of that chain with that first piece of research. The conversational AI system, RoboDoc, and its mission to fix what is, frankly, a terrible user interface problem in medicine.
We have to start there because it's the fundamental challenge the sources identified. You have these brilliant, highly specialized medical AI models. I mean, models that can achieve, say, 98% accuracy in detecting some rare disease.
Which sounds amazing.
It is amazing, but they often just gather dust in these academic silos. They never actually make it into the clinic. And the question is why? Well, it's because their user interfaces are just awful.
I see this in every single industry. You build this incredibly powerful, specialized engine, but if using it requires the user to, climb this massive learning curve, adoption just dies on the vine.
That's it, exactly. I mean, put yourself in the shoes of a clinician in a busy ER.
Yeah.
You need a fast result, a precise result. Now, if using the AI model means you have to know exactly which diagnostic parameters to pull from the chart.
And manually.
Then you have to format them into some specific file type, run the model using some clunky software, and then try to interpret this highly technical numerical output. That friction, even if it only adds, say, 3 minutes to the process.
That's a deal breaker.
It's a huge barrier. It's just faster to rely on your ingrained human heuristics, which, while they're fast, we know are susceptible to all sorts of errors and biases.
So the solution that the RoboDoc prototype researchers proposed is, I think, genuinely ingenious. They said, let's leverage the accessibility and the flexibility of large language models and conversational AI, the CAI, to basically serve up these specialized models through a simple chatbot. Your interaction is immediately just a human-like conversation. It completely removes the need to understand the complex model on the back end.
It is the ultimate abstraction layer. It creates this high-level user experience, or UI/UX, that just It eliminates the need for the user to manually run the model or even know its architectural requirements.
So it hides all the messy parts.
And for you, if you're trying to get a handle on this, think of it like Simulink in MATLAB. That software lets non-experts manipulate these incredibly complex underlying differential equations just by dragging and connecting these abstract visual boxes.
You don't have to be a math Ph.D. to use it.
Not at all. The conversational AI here is doing the exact same thing. It's hiding all that mathematical and structural complexity beneath the surface of a simple human conversation.
Okay, I love that analogy, but here's where my skepticism always kicks in. If the chatbot is hiding the complexity, aren't we just creating a new and possibly less predictable black box for the clinician to trust? We're not just trusting the model now, we're trusting the LLM to route the request correctly and interpret the result correctly. How does RoboDoc manage that under the hood?
That is a crucial question, and the answer really lies in a specific technology choice. OpenAI's function calling API.
Function calling.
Right. So RoboDoc is acting as this intelligent shifter, or maybe a dispatch system, between all these different specialized models, and it's critical we distinguish this system as task-oriented CAI.
Okay, what do you mean by task-oriented?
It's not a general-purpose LLM like you'd use to chat about the weather or summarize the internet. It's a chatbot that is specifically engineered to execute predetermined, specific diagnostic tasks. And it does that by calling external specialized pre-trained models when it's triggered.
So the chatbot isn't trying to invent a diagnosis on its own. It's more like an expert coordinator.
That's the perfect way to put it. It's an expert coordinator. It uses the LLM's natural language understanding abilities to parse what the user is asking for, and then it automatically selects the correct specialized tool or function to run that request. And this all happens completely under the hood.
So the user just types in their request, and RoboDoc figures out, okay, this person needs the X-ray pneumonia model, or this one needs the diabetes prediction model, and just calls the right function seamlessly. And the real beauty here, from what I read, is the system's multimodal input capability. That just dramatically expands its usefulness. Let's break down those two main modalities.
Okay, so the first one, and maybe the most immediate in terms of clinical impact, is image-based input. Let's say a user uploads a chest X-ray, maybe looking for signs of pneumonia, or an OCT scan for an eye condition.
Right.
The very first step actually uses GPT-4 vision. This generative AI processes the image first to create a really high-quality textual description of the visual features it sees.
Now, wait a second. Why do that? Why not just pass the image directly to the highly specialized diagnostic model? Why the GPT-4 vision detour?
Because that text description, combined with any other context the user provided, that's what triggers the function calling API. It acts as an interpretive filter and a router.
Ah, I see.
The LLM translates the visual input into a structured trigger signal, which then calls the right pre-trained image-based diagnostic model. That model runs its complex analysis, and then the LLM takes the output, which might just be a number or a category, and translates that back into a natural conversational response for the user.
It's a double translation process. Human language and images go in, it gets turned into a model trigger, the model gives a technical output, and that gets turned back into human language.
Human language to model trigger to model output to human language. It's a remarkable bit of integration.
It is. Okay, so the second path is purely text-based input, which is usually where these models just choke on unstructured data.
And this pathway is essential for any kind of numerical or risk-based diagnosis, like predicting the risk of type 2 diabetes or heart disease. A user might type in some really unstructured text, something like, I'm a 45-year-old male. I have a history of mild hypertension that I control with diet. My latest blood work showed my BMI is 35.42, my HbA1c level is 7.2%, and my fasting glucose was 130.
That is a classic example of just messy narrative patient data. A traditional machine learning model would need a human to go in there, pull out those 5 numbers, normalize them, label them.
Precisely. That's the friction. The task-oriented CAI just handles this on its own. GPT-4 processes that natural language. It extracts the necessary physiological parameters, age, hypertension, BMI, the key blood markers like HbA1c.
Which is that long-term blood sugar measure.
Right, and the glucose levels, and it formats them immediately into a standardized JSON file. That clean, structured data is then fed to the specialized TensorFlow.js-based diabetes detection model, which is just sitting there waiting for clean input.
And then the chatbot delivers the result?
The model runs the risk analysis, and the chatbot gives the results and interpretation back in a friendly conversational format. It completely removes the need for the user to understand data structures or file formats.
So the LLM is doing the administrative heavy lifting, the data cleaning and routing, and it's leaving the specialized model to do the complex analysis that it was built for. That just dramatically lowers the barrier to entry for these incredibly powerful analytical models.
It does.
And this functionality leads us directly to the core conceptual contribution of that RoboDoc study, the strategic role of the triage component.
Yes. This is where the paper stops being just about a cool interface and starts being about a whole system design philosophy. The workflow is designed around a strategic cascade. An automated diagnosis must lead to an action.
Right.
So in the RoboDoc prototype, the researchers included a component, they called it a stub function, and it was designed to schedule medical appointments based directly on the diagnosis's urgency and severity.
A stub function. So you're saying it's not actually making real-world bookings in the prototype, but it's there to conceptually prove that the connection can be made.
Correct. It's a placeholder, but it demonstrates the system's intent. And while it was just a dummy function in the research, this capability shows the immense potential for seamless real-world integration. You could connect this to external scheduling APIs, like Google Calendar, or the big booking systems used by hospital networks.
And the key is that the AI would intelligently choose the right professional, a specialist pulmonologist for a complex X-ray, maybe, or a primary care physician for a borderline diabetes risk based on its initial findings.
Based on its diagnosis and its urgency assessment. And that routing decision, that is the critical step that formally defines the diagnosis triage human care pipeline.
It transitions the AI from just being a prediction generator to being a process automation tool.
Yes.
But let me challenge this again. Who takes the liability if the AI-driven triage system routes a high-urgency patient into a routine booking in 2 weeks because it made an error in that urgency assessment?
That is the essential, unavoidable question when you start talking about AI cascades. And the researchers are very clear that the accountability and liability remain with the human clinician, which is why the AI is designed as an assistant.
An assistant, not the authority.
Never the authority. But the system's design does try to mitigate this risk by defaulting to the safer error, which we'll talk about in depth later. Basically, prioritizing urgency when in doubt. But for now, the key takeaway is that this workflow, established in the RoboDoc paper, it validated this whole hybrid approach. Multimodal input, function calling to specialized models, and a final diagnosis-driven triage step. And that conceptual validation, well, that's exactly what the colon cancer researchers needed.
Which brings us perfectly to the subsequent research, the MEDDEX web application. If the RoboDoc prototype established the process architecture, the Cascade MEDDEX is where we see that architecture applied to a really high-stakes, highly complex diagnostic task.
Colon cancer detection from histopathological images using a vision transformer. This is absolutely where the rubber meets the road.
It's a clear evolutionary step, isn't it? It takes the structural principles from the triage prototype, that need for a robust, reliable diagnosis feeding into a decision system, and it applies them within an environment that's built for complex human clinical collaboration.
That's a great summary.
So tell us more about the MEDDEX architecture. It seems to serve two very different but related functions in what they call the medical decision-making phase.
Precisely. MEDDEX is built for what they call dual decision-making. First, it facilitates the human element. It's physician discussion-based. It acts as this secure, collaborative online space where doctors can upload complex pathology cases, share the images, discuss their opinions.
Like a digital water cooler?
A very sophisticated one, yeah. And they could use a group voting tool to reach a collective, relevant diagnosis. The doctor who initiates the case acts as a team leader, kind of structuring the brainstorming and narrowing down the list of possibilities.
So it's basically a digitally enhanced tumor board. It's designed to facilitate the human teamwork that we know minimizes individual cognitive biases and, memory overload.
Exactly. It's leveraging the wisdom of the collective, which is considered a clinical best practice. But then you have the second function, which is the explainable VIT-based system. This is the intelligent core that provides that initial diagnostic input that the human team then reacts to.
And the engine for that is the vision transformer model, the VIT, optimized for telling the difference between colon adenocarcinomas and benign tissues.
That's the one.
Okay, let's do a real deep dive into the vision transformer. In computer vision, I think most of our audience is probably familiar with convolutional neural networks, CNNs. What makes the VIT model, which was, adopted from natural language processing, such a disruptive choice for analyzing these detailed, complex medical images?
Well, the VIT represents a really fundamental architectural pivot in computer vision because it basically throws out the traditional convolutional filter approach. Instead, it leverages the same core attention mechanism that powers the state-of-the-art LLMs like GPT.
That still sounds so counterintuitive to me. How do you apply a model that was designed to read sentences to an image of human tissue?
It's surprisingly elegant. The system treats the image like a sentence. The first thing it does is divide the original high-res image into a grid of small, non-overlapping square regions, typically 16 by 16 pixels. These are the image patches.
And those become the words.
They become analogous to words or tokens in a sentence sequence. These 2D patches are then flattened into linear embedding vectors, which are then fed into the transformer encoder.
And once they're words, the attention mechanism can take over.
That's right. The multi-head attention mechanism inside the transformer then calculates the relevance and the relationship between all of these patches at the same time. And this is the key distinction from CNNs.
Okay.
Traditional CNNs use local filters. They build up an understanding of the image hierarchically, first edges, then textures, then shapes, but they often struggle to see the forest for the trees.
Because they're so focused locally, they might miss complex patterns or dependencies that are scattered across a very large high-magnification image.
Correct. The attention mechanism, because it analyzes every patch against every other patch simultaneously, is uniquely capable of capturing these long-distance dependencies and really rich contextual representations across the entire image at once. For diagnosing cancer, where the pathology can show up in these complex scattered tissue structures, that global context awareness makes the VIT inherently better suited than a locally focused CNN.
That makes perfect sense. I mean, histopathology slides are enormous and incredibly complex, so you need the model to be able to look at cell morphology in one corner and the tissue structure 3 inches away at the same time.
Precisely.
But of course, using such a heavy and complex architecture always brings up the dreaded data challenge.
It does. And the researchers, they identified a really critical flaw in this widely used public data set called LC 25,000. Numerically, it's huge, 25,000 images, but it's heavily augmented.
What does that mean, augmented?
It means those 25,000 images were largely just generated by rotating, flipping, and color shifting a mere 12,250 original images.
Ah, so it's high volume but very low diversity.
Exactly. And for a complex, parameter-heavy architecture like a vision transformer, that poses a really high risk of overfitting. The model might essentially just memorize the minor variations of those 1,250 originals instead of learning the generalizable patterns of cancer.
And if a model overfits, it gets amazing scores in the lab, but is dangerously unreliable when it sees a real new patient sample in the clinic.
It fails completely.
So what was MedDex's solution? How did they ensure genuine robustness and generalization capacity in the face of this data problem?
They use a really rigorous multi-stage data strategy. First, to boost the diversity of their training pool, they merged in 10,000 additional images from a completely different source, the DigestPath dataset.
Okay, so more diverse training data.
Right, a broader base.
Yeah.
But the truly crucial step, what I would call the gold standard for clinical readiness, was the external evaluation.
Which was using that entirely unseen third dataset.
Yes. They performed a rigorous external evaluation on 1,200 images from an entirely unseen third dataset, the EB HiSeg dataset. This dataset was held back completely. It was never seen during training or internal testing. And confirming high reliability on this third external dataset is non-negotiable. It's the only way to prove the model hasn't just memorized its training data. It proves it can genuinely generalize its knowledge to new, real-world clinical samples.
Without that step, it's just an interesting academic exercise.
It's not a deployable clinical tool.
Okay, so we've established the VIT model is immensely powerful and robust. But in a field as high-stakes as medicine, power without transparency is, well, it's useless. This brings us to explainable AI, or XAI, which is a necessary bridge to get this thing into a clinic.
It really is.
And I think we need to reiterate why explainability is so non-negotiable here. Why can't a doctor just accept a diagnosis if the model is, say, 92% accurate?
Because of liability, professional ethics, and at the end of the day, patient safety. A complex deep learning model is inherently a black box. If the AI says, this is adenocarcinoma, the clinician needs to know why. They have to understand which specific visual features, which cell clusters, which invasion patterns, which complex tissue textures led the AI to that prediction.
So they can sanity check it.
Exactly. That transparency is essential for the clinician to perform their final check, validating the AI's thinking against their own years of experience before they deliver a life-altering diagnosis. Without XAI, the system is just too risky to integrate.
The sources categorize different XAI methods, model agnostic versus model specific, local versus global, but the MEDDEX application made a very strategic choice. They chose LIME, which stands for Local Interpretable Model Agnostic Explanations. Why was LIME the right fit for their vision transformer?
This was a critical technical decision, and it's directly linked to the VIT architecture. A lot of popular visualization methods, like the widely used GradCam, they're model-specific.
Meaning they only work on certain types of models.
Right. They rely on calculating gradients associated with the convolutional layers in CNNs. But since the VIT is non-convolutional, it's attention-based. These traditional XAI methods, they just don't work efficiently or sometimes at all.
So LIME's core advantage is that it's agnostic. It doesn't care what's inside the box. It just observes the box's behavior.
Exactly. It is model agnostic. It treats the VAT as a complete black box and only studies its input-output relationship. Now, how it actually functions to explain a prediction is pretty clever, and we can use a simpler analogy here.
Please do. The concept of surrogate models and superpixels can get pretty dense.
Okay, so let's imagine the histopathology image is a giant, complex Lego structure. The VIT model, the black box, looks at the whole thing and says, that's a castle. For LIME to explain why it thinks it's a castle, it doesn't try to understand the VAT's entire blueprint. Instead, it just plays a simple game of perturbation. Yes. LIME creates slightly altered or perturbed versions of the image. Imagine if LIME just randomly removed or blurred small clusters of Legos, these clusters are called superpixels, and then it asks the VIT model, is it still a castle?
Oh.
Now, if removing one specific 16 by 16 patch of bricks causes the VT to suddenly change its mind and say, no, that's a spaceship now, LIME identifies that patch as being critically influential to the original diagnosis.
So it's basically asking, if I take this small part of the image away, does the model's confidence drop dramatically?
Precisely. LIME does this thousands of times in the immediate local area of the original prediction. And based on which perturbations cause the biggest change in the VIT's confidence, LIME trains a simple, easily interpretable surrogate model, like a local linear regression model, to approximate the complex VIT's behavior, but only for that single image.
And the output is the visualization.
The output is a visual explanation, highlighting the specific pixel regions, often outlined in red in the MEDDEX interface, that most significantly contributed to the prediction.
That level of transparency is really powerful, but if LIME is just an approximation based on a simple local model, why should the doctor trust the explanation? How do we know the LIME interpretation is reliable and not just, generated noise?
That is the critical skepticism you need in clinical science. And the MEDDEX team actually validated LIME empirically.
Yeah.
They ran a feature removal test, they took random images, they let LIME identify the most significant regions, and then they masked or removed those very regions from the image data.
And what percentage of the image did LIME typically highlight as being important?
On average, the diagnostically important regions that LIME highlighted covered about 31.56% of the total imaging area.
Okay.
Now, when those areas were masked, meaning the VIAS was forced to diagnose the image without the evidence LIME said was crucial, the model's confidence in its original prediction dropped substantially by a staggering 53.89%.
A drop of over 50%. Wow. That statistically confirms that LIME isn't just guessing, it's effectively identifying the actual diagnostically meaningful regions that the high-performance VIT model is genuinely relying on.
The explanations are validated, they're localized, and they're consistent.
And this validation is so vital because it feeds directly into the ultimate safety valve, AI-human conflict resolution. If the AI prediction, which is backed by its LIME visualization, disagrees with the initial decision from the human physician team,
The system does not override the humans.
it provides the data, but the doctor remains the ultimate decision maker.
Absolutely. The XAI explanation, that LIME map, it provides the necessary insight for the medical team to understand the AI's evidence base. They can then critically evaluate the VIT's prediction alongside their own expertise to decide, did the AI spot something we missed? Or did the model make an error? The AI system remains an indispensable tool that augments human judgment, but it is never the final authority.
Okay, so we've covered the conversational triage hub, RoboDoc, and the explainable, high-performance visual diagnostic tool, MEDDEX. Now we have to return to the central thesis of this deep dive, the conceptual link between them. The MEDDEX researchers cited the conversational AI prototype as a strategic reference. This is where we connect the dots and realize the impact of that initial triage work.
And this is more than just a polite citation in a bibliography. It was a structural citation. The VIT research explicitly adopted the underlying conceptual framework that was validated by the conversational AI prototype. They needed an architectural blueprint that moved beyond just the diagnostic component.
And the prototype provided it.
It provided it, the robust diagnosis, triage, human care pipeline.
This still kind of begs the question, though. Why would an advanced colon cancer detection study focused on histological image analysis need to formally reference a general prototype chatbot that's handling things like X-rays and simple numerical diabetes risk?
Because that conversational AI prototype, published in the GNRX Med Prototype Study, it solved a key conceptual problem for the VIT researchers by validating the hybrid process model.
Okay.
Think about it. The VIT team was building a system that integrated advanced image analysis with human-physician collaboration and voting tools. They needed proof that it was even feasible to combine all these different hybrid components successfully. Multimodal AI, risk assessment, automated routing capabilities.
And the RoboDoc prototype basically showed them how to structurally glue all those components together. It showed them how to transition the diagnosis into an automated action.
Correct. It proved the feasibility of the overall workflow integration.
Yeah.
And critically, this conceptual connection, it forces a broader taxonomy for medical AI systems. We have to move away from the simplistic one-dimensional label of diagnostic AI and toward a more complex and more accurate concept, AI cascades.
And this cascade model is what ultimately justifies the high cost and complexity of training a huge model like VIT. How does that cost justification work?
It's all about leverage and prioritization. Training a VIT model is expensive, no doubt, but you justify that expense by maximizing its utility. If the VIT diagnosis feeds into a triage system, the AI is effectively filtering and prioritizing the entire patient caseload first.
So it reduces the workload on the humans.
It drastically reduces the early-stage workload on the highly specialized human clinicians, the pathologists and the oncologists. The AI handles the high volume of initial screening and classification, which ensures that human expertise is only engaged when the case truly warrants complex, nuanced, personalized attention.
Automation handles volume, human experts handle complexity. It's a really optimized division of labor.
That's the economic justification. It's about cost-efficient clinical automation. And this strategic model allows the sources to challenge what they call the false dichotomy that has plagued discussions about medical AI for years.
The idea that AI must either completely replace the clinician or it's basically irrelevant.
Exactly.
Yeah.
That binary polarizing view is just rejected. The research we've been reviewing proposes this robust third model. AI informs the triage with a high accuracy prediction. The triage guides the urgency with process automation. And then, only then, do humans take the final, informed, highly focused step.
And what makes this third hybrid model inherently safer and more scalable than trying to build a fully autonomous AI doctor?
Well, it addresses inherent human limitations, and the sources explicitly reference Daniel Kahneman's work on judgment here. Human decision-making is so susceptible to cognitive biases, anchoring, confirmation bias, and maybe even more importantly, high variance or noise.
Nice.
You can have two highly qualified human experts, and they may arrive at two totally different conclusions, given the exact same data, simply because of context or fatigue or even their mood.
The human factor is the noise.
Precisely. Model predictions, especially from a highly validated system like MEDDEX, are much more consistent and reproducible. There's less noise. The goal isn't to replace the expert's wisdom, but to reduce the human variability that leads to misdiagnosis, and to focus that human expertise where it can apply its unique strengths, informed by the AI's consistent analytical output.
So the cascade is safer because the human is always the final check.
Right.
But it's more scalable because the AI handles the initial repetitive filtering.
That's the model.
Okay, but we have to anchor this conceptual discussion in some empirical reality. The VIT model is only useful if it actually delivers statistically robust results that prove its complexity is justified. Let's look at the quantitative evidence that supports MEDDEX's deployment readiness.
Absolutely. We mentioned earlier that the model had perfect performance on its internal test set. We should start there, but also recognize that this is only the foundation, not the real test.
It's the baseline.
It's the baseline. So on the initial heavily augmented LC 25000 test set, the VIT model achieved phenomenal scores: 100% accuracy, 100% precision, 100% recall. 0 false positives, 0 false negatives on that specific set. It's encouraging, but it mostly just confirms that the model trained successfully without any obvious internal glitches.
The real test is the generalization capacity on the external, unseen data.
Absolutely. The crucial results came from that external evaluation using the 1,200 images from the EBI-SEG dataset. And here the model confirmed its robust generalization capacity with a really impressive 92.17% accuracy.
92% on data it's never seen.
And an area under the curve, or AUC, of 0.976. This high AUC confirms that the model is extremely good at discriminating between cancer and non-cancer cases, even when faced with data it has never encountered. This level of performance is the key indicator of reliability that you need for safe, real-world clinical integration.
And was the complexity of the VIT architecture, the fact that it's a huge attention-based model, was it justified when you compare it against lighter, more traditional CNN models? Could they have gotten similar results with something simpler?
The data shows definitively that the complexity was justified. The VIT model is significantly larger, 327.3 megabytes, compared to lighter CNNs. However, its superior performance on the real challenge justified that size. The researchers did a comparative analysis. While all the models got near-perfect scores on the easy LC25000 data, their performance absolutely plummeted on the challenging, unseen EBI-SEG data.
How bad was the drop for the lighter models?
Models like MobileNet V2, which are designed for efficiency, they only achieve 53% accuracy on the EBI-SEG dataset.
53%? That's barely better than a coin flip.
It's a coin flip. In contrast, our VIT model maintained 92.17%. That difference is statistically enormous, and the superiority was rigorously confirmed by McNamar's test with a significance value of P0.0000.
Okay, for our listener, just walk us through why a p-value of 0.000 is such a definitive statistical statement here.
So the p-value in this context, it tells us the probability that the performance difference we saw between the VIT and the simpler models was purely due to random chance. A p-value of 0.0000, which is what you report when the probability is effectively zero, means the statistical test confirmed that the VIT model's vastly superior performance is a real, significant, and reproducible effect.
So it confirms that for this high-stakes task, that complex transformer architecture was absolutely necessary to get real-world reliability.
It was necessary.
And the constraint of the larger model size, which would typically slow things down, that's mitigated because the whole system is web-based.
Precisely. Since all the computation is managed on the server side by the Meddex web application, the physician only interacts with a web interface. They don't need specialized hardware. And the the time it takes to get a diagnosis remains rapid, only 0.016 seconds per image. That's more than fast enough for a real-time clinical setting.
So we have proven accuracy, we have statistical justification. Now let's look at user acceptance, which is the final barrier to clinical adoption. Accuracy means nothing if doctors just won't integrate it into their routine. Did the application pass the will doctors actually use this test?
It showed highly promising results based on the Technology Acceptance Model, or TAM, evaluation. The Meddex application was evaluated by 50 medical students, which is a key cohort representing the next generation of practitioners who are typically less resistant to tech.
Right.
And the evaluation focused on standard metrics for assessing a tool's likelihood of adoption.
And what were the takeaway scores?
The scores were high across the board. They scored high in perceived ease of use, averaging 4.21 out of 5, which means users found the system easy to navigate and operate. Perceived usefulness averaged 4.16, confirming that the user saw immediate value in the tool for enhancing their diagnostic skills. But the most important score?
Let me guess, behavioral intention to use?
That was the one.
Huh?
And it was the highest, at an average of 4.30.
Behavioral intention to use. That's the stated conscious plan to adopt the system. That is a powerful validation.
It is. It validates that the Meddex tool is not only accurate and transparent, but it's also user-friendly and highly likely to be adopted into routine clinical practice. It satisfies all the essential criteria for usability and deployment within that AI clinical cascade framework.
But let's pivot back to the LLM component in that triage layer. We discussed the risk of unpredictability. Despite all this success and validation, no system is perfect. What are the recognized risks inherent in deploying an AI cascade like this, especially when that crucial triage step relies on a conversational interface?
The primary risk, and the researchers highlight this repeatedly, is the inherent unpredictability and the potential for what we call hallucination in large language models. While the specialized models like the VT are highly predictable in their narrow task, that conversational interface layer, the RoboDoc concept, can sometimes introduce behavioral noise.
Especially during the critical routing and urgency classification stages.
That's where it's most dangerous.
So give us some concrete examples of those documented misbehaviors from the RoboDoc prototype testing. This is where we get real about safety.
The documented issues really centered on misclassification, particularly around severity. In one case, the specialized X-ray model sometimes produced a false positive, misclassifying normal lungs as having signs of pneumonia.
Okay, which is concerning, but a false positive is usually caught by the human clinician on review.
Right. But more critical was the issue related to urgency classification. In a separate test case, the system correctly diagnosed viral pneumonia, but then it incorrectly tagged the case as urgent.
Wait, why is that critical? If the diagnosis is right, isn't flagging it as urgent always safer than non-urgent?
Because viral pneumonia is often much less severe than bacterial pneumonia and typically does not require immediate emergency room intervention. The system got the pathology right, but it misinterpreted the risk level.
And if a patient is incorrectly routed to an urgent care facility?
It clogs the system, it wastes specialized resources, and it generates unnecessary cost and anxiety for the patient. And on the flip side, if it routes a truly urgent case to a routine booking, the outcome could be fatal.
So the AI got the diagnosis right, but the triage wrong. And that triage error is precisely why this cascade model needs to be perfected. What is the crucial mitigation strategy against these inevitable LLM errors?
The strategy has to be codified in the system's design philosophy. You must train the AI to make the safer errors. And in a medical context, the universally agreed upon safer error is typically a type 2 error. Classifying a non-urgent case as urgent. We saw this with the viral pneumonia example.
Because the cost of a type 2 error is usually just wasted resources, but the cost of a type I error missing a severe condition or calling an urgent case routine is a delayed diagnosis or even death.
Exactly. The human error we're trying to mitigate is the type I error. Therefore, the cascade has to be designed with an extreme bias toward overclassification of urgency. This will result in unnecessary workload and expense, that's the cost of the safe error, but it absolutely prevents the catastrophic outcome of delayed necessary human attention.
And you have to have warnings.
The research emphasizes that these systems must be deployed with clear, persistent warnings, reinforcing the fact that the AI system is an assistant, and its output, especially the triage step, always requires human review.
Okay, let's unpack this and bring it all together for you, the listener. We've seen these two research streams, a conversational, function-calling triage prototype and an explainable, high-performance visual diagnostic engine. The synthesis of these two is the real moment of insight.
The power of the future model is in combining them. You get the reliable, explainable image diagnostics from the VitLime system, backed by that rigorous external validation, 92.17% on unseen data.
Yeah.
And you integrate that seamlessly with the flexible conversational triage layer that was exemplified by the RoboDoc concept.
And you deploy all of it through a web application, which removes the hardware constraints and immediately facilitates human collaboration.
That convergence provides the structural scaffolding you need for safe, high-volume automation.
So if we connect this to the bigger picture, the conceptual contribution we trace today, the structural citation of the triage work by the diagnostic researchers, it confirms a complete shift in purpose for medical AI.
It confirms the core takeaway, which is the shift from that polarizing, unrealistic goal of AI replacing clinicians to AI structuring and orchestrating the clinical workflow through diagnosis-driven triage. This hybrid pipeline is fundamentally how you reduce costs, how you mitigate that variability or noise in human judgment, and how you achieve scalability safely in modern healthcare. It formalizes the acceptance of the AI Cascades taxonomy.
And this means that success can no longer be defined just by predictive power.
Absolutely not. The most profound finding from this convergence is the realization that AI needs to focus just as much on process orchestration, the routing, the scheduling, the urgency assessment, as it does on pure prediction.
Right.
Since analytical models like VIT are demonstrating reliable, low-variability diagnosis, the next major frontier isn't just trying to squeeze diagnostic accuracy from 98% to 99%. That's just incremental.
So what is the revolutionary frontier then, if it's not accuracy?
The revolution is perfecting the automated triage and urgency routing logic to ensure that human expertise is only engaged when and where it is most critically needed. The success of the VIT model, even with its phenomenal 92% accuracy, is meaningless if the conversational cascade layer that receives that prediction makes a mistake, and routes a critical case to a non-urgent booking.
Or, conversely, if it creates so much noise with false alarms that physicians just start ignoring the system entirely.
Precisely. The reliability of the diagnostic engine is now just the cost of entry. The sophistication of the triage mechanism is the competitive edge. The system has to be robust from end to end. The focus is now on the operational efficiency and the safety of the process itself.
And this raises a really important question for you, the listener, to mull over as you think about the future of healthcare technology. If the goal shifts from pure diagnostic accuracy to overall workflow management and error mitigation, what new metrics, besides traditional accuracy and AUC, should we prioritize to validate this new era of AI clinical cascades?
Should we be measuring the time saved for human experts per week, the reduction in unnecessary referrals, or maybe the success rate and the safety profile of the automated urgency routing logic itself?
That decision, how we choose to measure success, will define how we build the safer, scalable healthcare systems of tomorrow.
A lot to think about.
Until next time, keep digging deeper into the data and challenging those false dichotomies.
We'll see you for the next deep dive.